OpenFest 2024. Back to the source.
Welcome back. We can start with the next lecture, and I'm going to present to you Sergei Golubchik, who is going to talk about MariaDB Vector, a new feature in MariaDB about search as far as I know. So I think it's going to be interesting for everyone. So let's run some applause for him and let him speak.
Hey, so I'm start from asking you something. Could you please, especially those in the back, move? There are lots of places in here, and I don't see anything over there. So if you'll try to raise your hand, ask me a question, I will ignore everything in the back because I just don't see them, don't see you. So just please, everybody move forward. Thank you. I'll start with introductions, so you can still move. I won't say anything important now. So this is the talk about MariaDB Vector. This is a new feature about MariaDB 11.7. So I said introduction. So my name is Sergei Golubchik. I'm MariaDB Chief Architect in MariaDB PLC and also a board member of MariaDB Foundation. I was working on MySQL as MySQL core developer since 1998. Well, that's before MySQL DB was created. And after acquisition, I moved to MariaDB, and I'm, MariaDB core developer since then. So what I'll be talking about? I'll be talking about MariaDB vector search, and yes, as a matter of introduction, what is the vector search? Vector search is the technology, and sorry if I'm saying stuff obvious to some of you or half of you. It's a technology behind such user important features such as semantic vector search. It's when you describe, like in normal language, what you want to see, find, and the engine finds you documents about text about what you need, not looking for specific words, but looking for meaning of the text. Or image search, or music search, or hybrid searches when you have text and image and music all together, and you use, I don't know, text, image, or music to find them, like you whistle in the microphone and you get an image about what you've just whistled about, or you write a dog and you find an image of the dog. And hot topic today is RAG, retrieval augmented generation. It's when you use a generative AI, but not a generic pre-trained model, but specifically tailored to on your data, on your text to answer a specific user question. This is all works using vector search in the background, invisible for the users. How this works? Well, on the conceptual level, it's very easy. You have your images or audio or text. You convert everything into vectors. This is where the magic happens, but there are already well-established techniques of how to do that. Then you store the vectors in the database. When the user wants to find something using, again, text, images, or audio, you convert the user query again into the vector. Then you have a database of vector and a vector to find in the database, so you just use vector search. And a couple of more points before I can start with actual content of the talk. What is a vector? The vector is just a list of floating point numbers, like this on the slides. Unlike, coordinates on a plane or on the Earth, the vector, those vectors are usually longer, 20 to like few thousand numbers in one vector. And when you search for vectors, the idea, what means that you're searching for the vectors which are closest to whatever user wants to find, to the nearest vector. And how the nearest is defined depends on how these vectors were generated. I'll talk more about that later. And one need to remember the search is always approximate, unlike if you look for coordinates, like, McDonald's closest to your house, that's usually done using exact search, but with lots of components in one vector. To my knowledge, there are no practical exact algorithms for finding nearest vectors, so the search is always approximate, and then you can decide how approximate you can allow it to be, and you'll see that later during the talk. And the last bit before we start, I'll be using this combination of letters M, H, and SW later in the talk. It's in the names of the variables, so I need to explain what it means. This is the vector search algorithm that MariaDB is using, at least at the moment. H and SW, it's hierarchical navigable small world. This is an industry standard vector search algorithm that pretty much every known vector store implements now. I'll be doing benchmarks. I'll be showing benchmark results later. Every single vector store, every single vector database that I use in benchmark implements this exactly algorithm. It's just currently the best when you compare like speed and precision, how good results it delivers and how fast it is. That's basically the best one at the moment. So this is everyone is doing that. There are other algorithms, some database, PG Vector implements a second one as well, which is faster, but well, less exact. But this one is basically the standard. And we in MariaDB use a modified version of it. That's why the letter M, and you can think of this letter M as MariaDB or modified, it's up to you. But this is what this algorithm name means. And let's start from the example to see how it can be used. I'll show two examples. First, this will be low-level example how you directly use the vector search in MariaDB using Python. First, we need to create a table. And there is nothing really surprising here. You just create a table. You create a column named vector. This one. And then create a vector index over the vector column. This is really what people would intuitively expect, and no real surprises here. You can configure the vector index by specifying parameters when creating the index, and I will explain later what they mean. Now, note that our vector length here specifies the number of components in the vector, and 1536 is a very typical number. You will see and recognize it. If you generate these vectors using OpenAI API, OpenAI returns vectors of 1536 numbers. That's where the number is coming from. So I mentioned OpenAI. So in this example, we'll be using OpenAI to generate vectors or embeddings. In Python, this is pretty easy. You just, this small Python snippet directly from OpenAI documentation. You just specify the model, the text, and this Python model will query OpenAI and return you an array in Python with all those numbers. 15,036, 1536. Now, when we have this number, we can insert it into the table we just created because we want to have a database of embeddings. So import MariaDB uses MariaDB connector Python. We get the embedding using OpenAI like on the previous slide and insert it into the database. Nothing particularly surprising here. Two things to notice. We convert the vector, the array, Python array into string representation with square brackets and numbers and commas. And we use the function vec from text on the MariaDB side to convert the string representation back into binary vector inside MariaDB. This works, but this is a little bit redundant. Like you have already vector in binary. Why would you convert it to text in Python on the client side? Then you send much larger amount of data to MariaDB. Then you convert it back to binary. So this can be optimized, and you can send the vector directly as bytes, as binary bytes to MariaDB, saving on, two conversions and less network traffic. So, but both will at the end have the same result. This is just a little bit more optimal. Then we do this many times for different documents. And when done, we want to search. And search is done, again, the same. This is MariaDB connector Python. And to search for the nearest vectors, we want to find, say, 5 nearest vectors, and to return 5 nearest something in SQL, you just do order by distance and limit 5. This is a normal SQL way of returning 5 nearest anything. And this works exactly the same with vectors. They are not different from anything else in SQL, at least in MariaDB in this regard. So you just order by vec distance cosine in this case, and then limit 5, yeah, you get 5 closest vectors. Note that this uses vec distance cosine, and when I've created the table, I also specified distance equals cosine because the index is built for this specific distance. And if you use a different distance here, you'll still get your results, everything will work, but optimizer will not be able to use the index, so it'll be slower, it'll just be a full table scan. Yes, so this is example how to do vector search in MariaDB, how to create the table, populate the table, and do the vector search for nearest vectors using directly doing SQL queries from Python. Normally people don't do that, they use AI frameworks, and out of them Llama Index already has support for MariaDB vector search. So to use MariaDB vector from Llama Index, you just need to import an appropriate vector store MariaDB, then you create vector store in Llama Index, and then you use it like any other vector store in using any normal Llama Index code, and then it's nothing different done from there. So there's no full example for Llama Index, but this is how that works with Llama Index. Yes, so this is how you use MariaDB vector. Now let's see how to tune the vector search inside MariaDB to perform and deliver good results. The first thing I want to point out when speaking about vector search tuning is hard. There's complex algorithms inside, and they have lots of tuning parameters. Some of them are explicit, some of them not explicitly mentioned, but there are still implicit assumptions, and they can be made into tuning parameters. And it is really impossible to describe to users what they mean unless you actually go through the trouble of reading the original research paper and then read the explanation of every parameter does and about what implicit parameters are there, and users are not going to do that. And there's also a very implicit and very complex and unobvious interaction between parameters. You increase something, then performance drops, for example. Then you decrease something else and performance goes up again, and then all in an obvious way. And we didn't want to subject our users to this, complexity. So our solution in MariaDB was we hide all that, and either we select we do implementation of something that doesn't depend on these parameters, or we find optimal values by numerous multi-week benchmarking and testing on different data sets. And if that's not possible, there's no optimal value, then we auto-tune it so that it just automatically adjusts to be, the most optimal value for the given settings. There are only 4 parameters left which MariaDB cannot auto-tune because they require conscious human decision of, how to make the trade-offs. These are those 4 parameters, and I'll go to explain each one of them one by one on the following slides. So the max cache side, the thing is to understand this original HNSW algorithm. It was designed to be in-memory algorithm, so it works the best if the whole data set, all the vectors, the whole vector index fits in memory. If it doesn't, it will still work in MariaDB, but it'll be slower, and depending how little memory you have, it can be much slower or a little bit slower. So the max cache size limits how much memory this index will use in memory, and it's safe to set it as large as possible because it will not grow to all that memory at once. It will grow as needed, and in my benchmarks, I always have set it to 10 gigabytes, and I never had it seen more than 2 gigabytes because I don't have that much data to grow over 2 gigabytes. So it didn't use all the 10. But again, of course, MariaDB cannot tune this automatically because MariaDB doesn't know how much memory you want to save for in a DB buffer pool, how many other applications you run that also need memory. So this is something that a person needs to decide how much memory can be dedicated to vector indexes. Then there's a distance, which is a parameter for index creation, this one. But also, if it's not specified when creating the index, then it's taken from the variable default distance. There are two distances supported, Euclidean and cosine, and it's not really a tuning parameter. It depends on how the vectors were created, because the trick when generating vectors is when you convert anything into vectors, the whole idea is that if you have two images or, I don't know, song fragments or two text, if they are similar, like logically, like text about the same, images have the same, I don't know, similar looking dogs, or then those vectors should be close to each other. If they're different, vectors should be different. So, and vectors are close using some specific distance. So here you need to specify the distance that those vectors were generated for. You can generate vectors that will be close for similar text in Euclidean space, but not close in cosine or vice versa. Basically, you're not using it to tune the algorithm. You use it to tell the MariaDB for what distance your vectors were generated. And I'll have benchmarks for different distance functions, but this is basically, you just you use, for example, OpenAI to generate vectors. Then you tell MariaDB that this vector should be used. Well, OpenAI vectors are normalized, so you can use either. It doesn't matter. But for other LLMs, for example, you need to use a specific distance that those vectors were designed to be used with. And these are two truly tuning parameters for the algorithm, and they allow you to decide on trade-offs. What trade-offs do you have? So they both behave the same way. The algorithm, the search can be rather fast, but then it will be not very precise and very far from exact search. It will deliver results that are not very good. Or it can be very precise and very slow. And then you want to decide how much of precision is required, and how much of speed is required, and how much of precision you want to trade for speed, or the vice versa. And after you decide that you need that much precision and none less, so you need to do that much work to actually, reach this precision. You can still decide where you want to spend to do this work. You can spend more time when you build in the index, when inserting the data into the table. Then you get a very good index, and then you can search the index very fast and get good precision. Or if you need fast inserts, you can spend less time during inserts. Then you get the index that is not very good. And you can compensate for that by spending more time during the search, doing more thorough search, and still get good precision. So basically you have two degrees of freedom, 2 dimensions, whether you want fast and imprecise or slow and precise, and whether you want fast inserts, slower selects, or slower inserts and faster selects. And that's why you have two variables, so that you can tune in both directions. This is how typical, trade-offs look like. So I'll be showing benchmarks in a minute, and those will be the charts on benchmarks as well. This is the time to build the index, and how recall depends on building time. On the x-axis you have the recall, which goes up to 1, and 1 means that algorithm delivers exact, accurate results, absolutely exact. And recall cannot be greater than 1. And some papers call it precision, but it's usually called recall, but I'll use those terms interchangeably. 0.7, that's 70% means, I don't know, you do limit 10, and 7 rows out of 10, 7 vectors out of 10 are indeed one of those 10 closest, and 3 are somewhere further down the line, so 6 is and so on. I've seen in the papers that a practical good recall is considered to be like 95%. I mean, for reg, it probably doesn't matter if you are 99 or 98. So everything above 95 should be good. 70% or 60% is not very useful. And on the y-axis, there's just time to insert all the data in seconds. So what you can see here, as M is increasing, recall increases, but the build time increases as well. And up to M equals 8, this build time is increasing a little, and this recall increases significantly. And then there's a point of like diminishing return. You get a huge increase in the build time for a little bit better recall. And the next chart shows how the search time depends on the index parameters. Again, this is recall on the y-axis, on the x-axis, and 0.3, 30% is completely unusable recall. And as you can see, as M increases with the same EF search equals 10, recall increases, improves, and the search becomes slower. And then I thought that M equals 8 is as slow build as I want to go. So I don't want to have M greater than 8 because then inserts will be too slow. Then I started increasing EF search, and then you can see again, recall started to improve, continued to improve, and search continued to drop, but a little bit faster. So this is a typical trade-off you will have while tuning the index. You can have it either fast and imprecise or slow and precise. So those were just example charts, not corresponding to any real data. And now I'll show real data performance comparison with other vector stores, vector databases. I was using N benchmark toolkit for approximate nearest neighbor vector search, and all the vector databases they support. So this was MariaDB, pgvector, and Quadrant Research and VV8. Quadrant and VV8 are dedicated vector databases specialized specifically in vectors, and Redis search is vector search for Redis. So those slides show a small data set. It's simple and small, 60,000 vectors of about 800 dimensions each, Euclidean distance. What you can see here, looking on the left slide, this is build time versus recall, as I've just shown a few slides ago. MariaDB is the fastest here, like pretty much on all recall range. It's twice as fast as Redis, no, 3 times fast as Redis, twice as Quadrant, and Postgres is somewhere there. On the other hand, if you look on the QPS, then Redis is a little bit faster, up to 99%, then MariaDB is faster, and everything else is so much slower that, well, I won't even name databases down there. This is the larger data set. It has 1 million vectors of almost 1,000 dimensions. And again, on the index build time, MariaDB is still the fastest, has the smallest build time, up to, what, 99%, 98%, and then Quadrant is getting better. On the other hand, on the search time, MariaDB is second after the Redis, and Quadrant, pgvector, and VV8 are much slower. On the other hand, Redis is much slower on inserts than MariaDB. So on the total comparison, I think still MariaDB is kind of good here. And now I'll show one more data set. It's not that big, but it's hard, and it's difficult to search in. As you can see on the QPS part of the slide, Redis doesn't even reach 90% recall here. It just drops earlier and cannot reach 90%. So I would think that qualifies Redis is unusable for this particular data set. This is New York Times articles using cosine distance measure. On the other hand, yes, and MariaDB again is fastest or second after Quadrant on the build time, and it's solidly the best on the QPS side, starting from 88%, I think. So for 95, which is, I think, which I said, I think is the practically usable recall level, Again, MariaDB is much better than everything else. It's probably, I would say, 1,1700 queries per second, while everything else is something about less than 500, like 300 QPS. So that gives us 6 times, approximately, by just looking at the graph. I don't remember the numbers. So those were benchmarks, and I think I'm getting very quickly to the end of my presentation, which is, yeah, there will be more time for questions. This is so as a summary, what features MariaDB has, MariaDB vector has. MariaDB has implemented a vector data type. It already exists, it's in MariaDB. It supports both text and direct binary input for improved performance. There's vector index type using MHNSW algorithm. It supports 2 distance functions, Euclidean and cosine, so that you can tune the algorithm to your application requirements. There are 2 tuning parameters that gives you 2 degrees of freedom. I mean, and everything else is hidden and automatically decided on. And all that together delivers, I would call, a very comfortable performance compared to other vector and non-vector databases. 2 more features that need a little bit more talking about. MariaDB vector supports combining vector search with the where clause, doing fully normal SQL semantics, that is, where limit is applied after where, meaning if you do where clause and then limit 5, you'll get 5 vectors that match the where clause. It sounds obvious, and this is, of course, what everybody intuitively expects how it should be, but it's very rare in the vector databases world. It's called post-filtering. Almost no vector database supports it. I've read in the documentation that pgvector has it implemented and will have it, and they have it supported in the next version 0.80. Otherwise, in all those others I've had in benchmarks, I didn't try, but I've looked through the manual, and none of them supports that. The reason is that vector search algorithms, all of them that looks for approximate nearest neighbors. The problem is called K approximate nearest neighbors. That is, all algorithms for vector search look in a way, give me this many nearest neighbors. And they'll find you this many, like 5 or 10 nearest neighbors. And if you apply the where clause after finding 10 neighbors, you might have less than 10, like 5 or 1, or maybe none of them will pass the where clause. And that's why vector databases don't support this intuitive thing with the where clause with the SQL semantics, and MariaDB we support it. And pgvector will support it in the next release as well. Also, we have compact indexes with only 16-bit precision per vector component. It gives us half the size for the vector index and half the memory requirements as compared to if we would be using 30-bit floats like many other vector databases are doing. And this is here important to mention that this is not half-width floats, like pgvector has half-width floats in the 0.70, and Ready-Search has 2 formats for half-bit floats. One of them has 8-bit precision, the other one has 10-bit precision. And pgvector has FP16, which has 10-bit precision. So if you go down to 10 or 8, even 8-bit precision, this is just too much of precision loss. And you save space, but it really affects the recall. You can see on those charts that recall drops. And that's why it's always a trade-off, whether you want to save space, but then have worse recall. The way it's implemented in MariaDB, we have full 16-bit precision, and recall loss is about 0.1% or less. And speed up is like 20–30%. So there's no trade-off here. It's not configurable. It's just always enabled because you don't lose anything by using it. And that's one of the examples how we do not force the user to make difficult decisions, whether you want small index or you want fast index, and or do you want index that delivers good results. You just have everything and that's why there's no option for that. This is the first release of our MariaDB vector search, so it expectedly comes with some limitations. Currently, you only can have one vector index per table, and it cannot index null values. It only works on InnoDB, MyISAM, and area storage engines. It doesn't support partitioning and doesn't support XA. And we plan to work on removing those limitations. But first and foremost, we want to concentrate efforts on making all those popular AI frameworks to support MariaDB, because this is what we believe people are using. So we need to make sure that those frameworks like Llama Index already does, but LangChain, we want LangChain to support MariaDB, we want Spring AI to support MariaDB, we want LangChain for J to support MariaDB, and so on. So this would be our focus of efforts, in the most near future. But then also we plan to add more distances, like Hamming distance or Jacquard or L1, or more vector search algorithms perhaps. This all depends on what users will be asking for. We definitely need to improve observability, to add more status variables or information schema tables or performance schema tables to give users better understanding of what's going on with their vector indexes, how much memory, for example, the index is taking at the moment, and what index, and so on. This is all, there's not good, observability now is not very good, so we want to work on that. And of course, we still want to add more performance, implement what other vector databases call pre-filtering, although in MariaDB case, of course, there will be no difference for the user between whether it's pre or post or whatever. It'll be just a normal where clause, and optimizer will automatically decide what kind of filtering to use internally for the best results and best performance. Then there's quantization, another technique for improving performance. We're also thinking of that. And of course, we want to remove those limitations I've just listed on the previous slides. Those are our plans for the future. And yes, everything I've talked about except for the last slide of future ideas. Everything else is present in MariaDB 11.7.1, which was supposed to be released this week, but some people surprisingly don't work on weekends, so it'll be released next week. Thank you. Yeah, this is the feedback QR code that organizers wanted me to put on the slide, so you can scan it and provide some feedback. And if you have any questions, I'd be happy to answer them. Thank you.
Thank you.
Any questions?
Whoever has a question, over there is the mic in the middle of the room. So you can go there, ask the question, so the people on the stream can hear you as well.
Hey, so as far as I understand, you can produce the vector in some kind of model outside Maria, and then you insert it. Is there, and do you plan to add some kind of a way to connect the model to produce the embeddings and inject the data in the vector index? Or do you plan to rely mostly on frameworks like LangChain? Thank you.
Yeah. So the question was, if we think in MariaDB about skipping this step and letting the users insert the documents directly into MariaDB and let MariaDB take care of converting the documents into embeddings. Yes, absolutely. So we do think of that, and people ask us about that, and I've seen blog posts saying that this is an important feature. I also think it's important for those frameworks because you don't want to stop using, I don't know, LangChain if MariaDB can do this automatically. But I would prefer LangChain to know that MariaDB can do that automatically, so that you can still use LangChain and let MariaDB do the work for you. But you can also do that inside MariaDB. So yes, this is we talk a lot about this, and considering how much we talk about that, it likely we'll get it, well, sooner than later.
Thank you.
Two questions from me. First one is the database optimized for certain vector sizes? Like if we have larger vectors, does that pose a problem in performance? And the second question, okay, yeah.
Okay. So the question is, for what vector sizes MariaDB is optimized? Currently, there are no optimizations that specifically depend on the vector size. That is, I mean, the search in the vector, it contains a big number of calculation distances between two vectors pairwise while it's searching. And distance calculation, it's operation linear on the vector size. So if you have longer vectors, the search will take slower because the vectors are longer, there are more numbers to process. Well, I do have some optimizations in the work that are specifically tuned for long vectors, but then they're not part of this release. Well, they were not good enough to show the good performance. But so at the moment, there are no optimizations that depends on the vector length. Basically, you can use the vector of any length, and just the longer the vector, the slower it will be because the vector is longer, because there are more data.
Okay. Second question, I guess I may have missed something in the beginning, but do you need to rebuild the index after inserting some stuff, or does it update on insert? When adding new vectors to the database, do we need to explicitly do a rebuild of the index, or?
No.
Yeah.
Yeah. So the question is if one need to explicitly start some kind of indexing operation. No, this works like any normal index. The vector index is not special in this regard. After you create the table with the vector index, you can just insert and data will be in the index. Or you can insert first and then do alter table, create index, add index after that. You can do either way. Also, you can, of course, do updates and deletes. This is also all works normally.
Okay, thank you.
Hi, Sergei. So, two questions from me as well. The first one a bit more high level. I mean, if I'm looking for a vector database, why would I go for MariaDB and not like pgvector or Chrome or whatever is there already available?
Well, I'm of course biased, but you can go for MariaDB and not pgvector if you want better performance or better recall for the same performance or better performance for the same recall. But on the other hand, I would think that there won't be a question if there are people who already use MariaDB and want to start using vector search functionality.
Yeah.
They won't be asking this question, they'll just start using vector functionality inside MariaDB. So this is the easiest for them to start using vector search. If you're starting a completely new project, then of course you need to go for the database that provides you better performance. So this is MariaDB. But for example, if you need features that we don't have yet, then yeah, there are other vector databases that.
Yeah, and thanks. And so the second question, kind of in the same context, I mean, if I'm already using MariaDB and the MariaDB tooling around it, for example, backups, how the vector database is.
How what?
I mean, if I'm using Maria backup
Yeah.
for the rest of my databases at the moment, what are the specifics using vector databases with anything there that needs to be considered?
So the question there is, if somebody is already using MariaDB and like this, Maria backup already used and all those, I don't know, scripts monitoring around that, what one need to keep in mind when starting to use vector indexes.
Yeah.
It's difficult to answer because this feature is new and nobody is using it yet. So in our testing, Maria backup works. We do have tests that you can do Maria backup of table with vector indexes and then restore and everything works. But
So
if there will be any practical problems with that, if there are any practical problems, then our testing did not find that yet.
Okay.
So
So it's already supported in.
yes, Maria backup works.
Okay. Thanks.
Thank you. We still have time for a couple of other questions. Yep.
Hello. Hello. Is there any benefit in doing batch inserting when we're indexing, or we can do one by one?
Yeah, thanks. The question was if there's any benefits of doing batch inserts. At the moment, no. Rows are inserted one by one, and batch inserts do not improve anything whatsoever. There is a task in our feature tracker to make use of that based on the idea that after you've, well, if you have a populated table and you can run, I don't know, optimized table, then you already know all the data in advance, and perhaps it could help to create a better index if you know all the data already. But this is just on the level of ideas, and there's no clear understanding in how to use this information yet. So at the moment, there's no benefits if you're doing batch inserts or just row by row.
You can do alter table and run at the same time. So you have the benefit, you can use the table while the vector index is building.
Yeah, but so yes, if you do alter table add index, then the table is still readable while the index is being created. So it's not locked for the time. Yes, this is true, but the question was if batch inserts, well, are better for, well, vector indexes. And at the moment, no, they are exactly the same.
Okay, anyone else? Okay, a round of applause again
Thank
for
you.
Sergei.